Now let's take a closer look at motion in 2 and 3 dimensions. So for now we're going to assume that r of t is the position function of some object. In which case we know that the derivative is going to be the velocity of that object. Now remember, velocity is now a vector. In Calculus 1, when you look at velocity as a derivative of position, it's more or less just a signed real number. But now it's a vector. It makes sense to talk about its magnitude. And the magnitude of your velocity is just your speed. And then the derivative of velocity is now your acceleration vector. Well, let me just go through a quick example. Say where r of t is 2 cosine t, 2 sine t. So this is the motion of an object in a circular path. So then the velocity looks like negative 2 sine of t, 2 cosine of t. And if you draw that velocity vector on this path, well, say when t equals pi over 2, you get a vector that looks like this. When t equals pi, you get a vector here. And so you get these vectors that are tangent to your path. Now the speed is the magnitude of r prime. So it's the square root of, well, negative 2 sine t squared plus 2 cosine t squared. And usually the speed of an object that's moving in this way is going to be a function of t. But in this case, we're going to end up with 4 times sine squared plus 4 times cosine squared. So in fact, you get a constant speed in this case. So the velocity is changing, the direction that the object is moving is changing, but it's traveling around at a constant speed. The acceleration is r double prime. That's going to be negative 2 cosine t, negative 2 sine t. Notice that that happens to be just the opposite of r. So what that means is that at every point along this curve, if you look at the vector from the origin to where you are, well, the acceleration points from where you are to the origin. So your acceleration vectors all sort of point inward here. Okay, now this example reveals this interesting phenomenon where you have an acceleration that is non-zero, but your speed isn't changing. And this is one of the fundamental differences between motion in 1 dimension versus motion in 2 and 3 dimensions. So in 1 dimension, acceleration always changes your speed. Right, you have an object that's moving along some straight line path from left to right at some speed, and your acceleration, if it wants to make you change direction, the only other direction it can make you go is backwards. And in order to do that, it has to slow you down and then start making you go backwards. But now in 2 dimensions or 3 dimensions, acceleration now changes 2 things. It changes your speed and or your direction. And so it's kind of useful to figure out how much of your acceleration is changing your speed and how much is changing your direction. So what we're going to do is split acceleration up into two pieces. We say that your acceleration it has a tangential component. That's the speed changing component. Or we call this the tangential component because the velocity vector, remember, is tangent to the curve. And so if the acceleration is also tangent to the curve, well, then that's going to serve to increase the magnitude of your velocity without changing the direction. And your acceleration also has a normal component, which is a direction-changing part. Okay, and so for the tangential component, basically what you want is just the projection of your acceleration vector onto your velocity. So if you want just to say the magnitude of the acceleration that does speed changing, well, then you would look at the dot product of your acceleration with your velocity divided by the magnitude of your velocity. And then the normal component is sort of what's left. Or if you prefer, you can look at the magnitude of the cross product of your acceleration with your velocity, and again divide by the magnitude of your velocity. This works because the dot product is in terms of cosine of the angle between the acceleration and velocity, whereas the cross product is in terms of sine of those two things. Well, let's go ahead and just work out a quick example. So let's say you have an object that's moving according to the position function. R of t is cosine of t, sine of t, t squared. And let's find the tangential and the normal components of the acceleration. And again, these are both going to be functions of t. So for the tangential part, well, for both parts actually, we're going to need r prime and r double prime. So r prime is negative sine of t, cosine of t, 2t. And r double prime is negative cosine of t, negative sine of t, 2. So I want to take the dot product of those two vectors and then divide by the magnitude of r prime. The dot product here on top, that's sine of t times cosine of t, with the minus signs kind of canceling, minus sine of t times cosine of t, and then plus 4t. On bottom, you get the square root of sine squared of t plus cosine squared of t plus 4t squared. Well, that all simplifies down pretty nicely. On top, you just end up with 4t, and on bottom, you have the square root of 1 plus 4t squared. Okay, so this is how much of the acceleration vector is changing your speed. If you wanted the actual vector component, sort of the vector piece of the acceleration that was speed changing, then you would want to take this component and then multiply by the unit vector in the direction of r prime. Now for the normal component, you want to first find the magnitude of the cross product of r double prime with r prime. So let's see, I have I, j, k, negative cosine t, negative sine t, 2t, and negative sine t, cosine t. Oh, sorry, that's just 2 here, 2t down here. Okay, well, this is going to be a bit of a mess, unfortunately. So you're going to get negative 2t sine t minus 2 cosine t for your I component. The j component is negative 2 sine t, and then plus 2t cosine t. And the k component will end up being negative cosine squared minus sine squared. So that's what the cross product is. Now you want the magnitude of all that stuff. Well, it's kind of ugly, to be honest. So maybe let's skip that. But in any case, you're going to take all of that stuff and then divide again by the magnitude of r prime, which is the same as it was before, square root of 1 plus 4t squared. Okay, so in principle, that's how you find the tangential and normal components of the acceleration vector.